In this video, we're going to continue working through this notebook and start trying to visualize a couple common discrete distributions. So we're actually going to start with the binomial distribution. So as a reminder, if x is a binomial random variable, this is the probability mass function, which is the probability x takes on a value k. Classic examples for binomial, I usually use coin flips, but it could also, there's lots of different options. So let's stick with coin flips. So in this case, I'm going to flip a coin n times. Let's say n is 10, and x is going to be the number of heads that I get, assuming the probability of heads on a given for the given coin is p. So what we're going to do first is actually hand code a function that will calculate this probability for each value of k that's in the support of x. And then we'll see how there's built-in functions that do this for us. I just want you to look under the hood this first time. So actually to do this, we're going to create our own function, binomial dist. And I actually would like to create an array where the first entry is the probability that x is 0, and the second entry is the probability x is 1. Instead of doing a loop, a for loop, I can actually do this much quicker with list comprehension. So the idea is I would like to be looping through k, and we're going to let k go from 0 up until n. And so I do n plus 1 because it's exclusive in Python of your endpoint here. And then I can put before this statement, I can put whatever I want to iterate each time. So each time I want to calculate this combination and then p to the k and 1 minus p to the n minus k. This combination is actually also built in as a special function. You can use scipy.special, and it's called binom. So that stands for the binomial coefficient. So if I do binom n comma k, it'll give me this n choose k value. And then I'm going to do times p to the k, and then times 1 minus p to the n minus k. And again, now I'm going to get, let's look at it here, we'll do 100. Now I'm getting an array that has 0 up through 100, so 101 entries. The 0th entry is the probability of getting 0 heads. If I did 100 flips, where the probability of 1 flip landing on heads is 0.4. Here's the probability of getting 1 head, 2 head. So you can see these are pretty small, then the probabilities get a little bit bigger, and then they get small again. And so we'll visualize this. But before we do, let's just think of how I could grab. Actually, let's visualize it first. Good call. Let's do that. We're just going to do a quick check that all of these add up to 1, which they do. I'm just off by basically floating point rounding error. All right, so to visualize, if you remember from the last video, because these are the probabilities, these are the heights that I want each of the bars to take. So I'm just going to use x.bar because I already know the heights. The input values, the x values, are just going to be all numbers starting at 0, integer values starting at 0 going up to 100. And then I will just do PMF for the heights. And here's my distribution. So again, if I wanted to zoom in a little bit, I could see maybe I go from 20 to 60 just because this is, there we go. And what I notice is that most of the values, it's most probable to get 40 heads, which makes sense because my probability of heads was 0.4. It's pretty unlikely to only get 25 or something really small, and it's less likely also to get like 55 or something bigger here. So if I want probability x is equal to 8, on this picture, I can't even see it. It's definitely super tiny because I'd have to zoom in really, really close to see it. But I could calculate it by going back up and grabbing the entry up here that corresponds. So not 0, not 1, but I'm going to go to that entry that corresponds to the probability is 8. And so that's going to be, I believe I called this prob. Yep. There's the probability. That's why I can't even see it. It's super tiny. And then similarly, if I want the probability x is less than or equal to 8, it's very unlikely, but I'd basically be summing all these probabilities that are not even showing up here because I don't even have 8 in the picture. We can go back to show you 8. But again, it's not even gonna show up here. It's so small. So if I want that, this is the sum of all the ones from 0 to 8, or I could even do all the ones less than or equal to 15. It's still a tiny, tiny probability. All right, so all of this we did by hand just to show you what's going on underneath the hood. But to make your life, oh, and let me fix this. This should say, I think, there we go. That's the notation. To make your life easier, I'll now show you the built-in functions that Python has for us. So first thing is its scientific computing library, SciPy, has built-in functions to calculate the probability mass functions for tons of different discrete random variables. In fact, if we click to this, you can scroll down and you can see a ton of them that are all built in. So this is going to be really useful anytime you want to plot or reference. So let's actually do this here. Let's recalculate given that this is my random variable, what's the probability x is 8? Let's use the built-in function here. And so the built-in function says take binom and then .pmf for probability mass function. And then you put whatever value you want. Here I want k is 8. And then I have n is 100 and my probability is 0.4. And when I calculate this, I'm getting the exact same value that we got by hand up here. All right, so PMF is really useful. Now, if I wanted to recreate the same array that we did up above, remember when we did this with this whole function here? If I want to recreate this, instead of writing this function, I can call the binomial.pmf or the binom.pmf with x as my input. So here, this is an array. I just had it be an array of size 10 to keep our life easy. So this is now just looking at the first 10 entries. But if I wanted, we could go all the way up. And then I'm going to get the same thing we did by hand. Again, if I want the probability that my random variable, I get less than or equal to 8 heads out of 100 flips, I'm summing the 0 through 8th entries of this array. But there is a built-in way to do this without having to sum separately. And that's because we have a name for this sum. So in general, we call this sum of these probabilities that x is less than or equal to a. That's equal to our cumulative distribution function. So that's the cumulative distribution function is the probability that x is a, or a minus 1, or a minus 2. For these discrete random variables, you'll just be adding up all of the values prior to a. And in this case, you can just do it all in one call. I'm doing 8, n is 100, p is 0.4, and that's summing all the values in the PMF up to and including 8. So in general, if you want to do a histogram for a binomial, you can just jump right to using the built-in functions to do it. You don't have to create your own. Again, I'm not using hist, I'm using bar because we don't have an array of data, we have the list of probabilities. So I'm just creating it directly. Now, here we know the exact distribution, but now let's do the same idea that we did in the previous video. Let's actually sample from this distribution and then plot our empirical distribution. So there are useful built-in functions in Python for sampling from a wide variety of distributions. Again, we can go to this random generator link, scroll down, and we're going to see tons of distributions we can draw samples from. So these will be very useful. And one of those in particular is the binomial. And so the syntax for this is np.random. But instead of choice, you actually specify binomial. Then you say, what's your n, what's your p, and how many samples do you want to grab? So we can do sizes. Let's start with 100 so it's not so big. So that took a random sample of 100 values based on this distribution, which means we're most likely to get values here around 40 because they have the highest probability, less likely to get values like 8 or 15. They have very tiny probabilities. And that's consistent with what we see here. All right, so then we can use this random sample, again, as an approximation of the theoretical. And you may be saying, well, why are we doing this again? So in general, right now I'm doing this to show you that if we didn't know the theoretical, but we, for example, we're out in the real world and I don't know what the underlying theoretical distribution is for, let's say, the height of students at CU, I could go and take a sample and then plot my empirical distribution of heights. And if I took a large enough sample, we're going to be able to say that empirical distributions should be really close to the theoretical distribution. Now, let's do it here. So I'm going to come plot. We're going to plot actually both. So I'm going to show you, here's my simulated ones. I actually did 10. Let's go back to 100 just so you can see. 100 here. Here's the theoretical one. We already plotted this above. I'm just copying it. And now I'm going to plot both of these right next to each other. So we have a good way of comparing. So this is a good example of where this figure and axis objects are helpful, because ax of 0 is going to be my first plot. Ax of 1 will be the second plot. And there we go. So here's my simulated one. Here's the theoretical. I think I'm using 100 here a lot. Let's do this so you can see what I'm doing. 50. Okay, so what you can imagine is I've taken 50 people in the class. I've given each of them a coin that's biased to be heads 40% of the time. And I have each of those 50 people flip their coin 100 times and count how many heads they got. And then we're plotting the distribution. That's representing the density histogram, or the probability distribution here of the number of heads. See, we can see it looks kind of like the theoretical, but there's a lot of variance and randomness in this because I didn't sample that many people. Or I didn't use that many people. If all of a sudden I'm like, okay, now let's do 1,000 people, it's getting better, closer. If I say, okay, 10,000 people, well, now it's looking almost identical. And as we go up to 100,000, my simulated distribution's basically identical to the theoretical. So this property is going to be useful in particular when we don't know the theoretical. We just realize now, as long as I sample enough, my simulated one should be approaching the actual theoretical. Now, let's see, in the case of the binomial distribution, we actually could have also simulated this using np.random.choice. And I think I did heads here. I gave you the values you're going to have on your homework, but I'll switch it back to what we're doing in this demo. So I could have said, let's randomly pick heads and tails according to this probability, and I will get the same distribution. I don't have the bins set exactly the same. That's why these look slightly different. But let's switch that here just so they look the same. But that was just mainly a special case because I have used coin tosses, or it's mainly a special case because of the binomial distribution. With Poisson, I'm not going to be able to easily use np.random.choice to simulate it. I'm going to have to use the built-in functions that are available in Python. Which actually leads us to the last part of this problem. So I now put this on pause and see if you can repeat this process for a Poisson random variable. In particular, I want you to come up with a simulated one and a theoretical one, and then play around, as you simulate more and more values to see how this will converge to the theoretical. But instead of doing binomial, let's do a Poisson with lambdas 3. And just a reminder, lambda and a Poisson random variable is good for modeling the number of events that occur in a given fixed time interval, assuming these events are independent and that they happen with an average rate of 3 events per time interval. So if I know, for example, that a certain car or certain intersection has 3 car accidents per month on average, I can then come up with a probability distribution for the number of car accidents we would expect in the next month. And I then am going to come up with values 0, 1, 2, 3, or probabilities for each of those values. So go ahead and play around with the built-in functions, and you can put this on pause. All right, I'm going to jump into the work here. So I basically copied and pasted the same code we had above. I just switched because the Poisson distribution just has the lambda input here. So here's my simulated one. And what I switched was I switched this to Poisson. And I also switched the bounds just because on average there's 3 per month. So I'm not expecting a huge, much more than 20. And we'll see. 20s, there's not a very big probability of 20. And then here's the theoretical. So I'm using Poisson.pmf, x, I'm putting that in here, and then my parameter, and that's going to get output here. And then I'm using a histogram for my simulated values and a bar for my theoretical values. And so we'll do this together. Now, I started with a low simulation. I only did 100. So you can see, I could even cut this off. We could even cut it off at like 15 here because we can see the likelihood of getting 12 or 14 is still pretty tiny. Yeah, so these don't match as much because I'm not simulating enough values. I'm not grabbing enough random samples. I could go to 1,000. It's looking closer, almost identical there. And then I'm sure if I go up to 10,000, yeah, they're indistinguishable from the eye. So same idea of what we did above, but just applying this now to a new distribution. And we'll use this idea of the empirical versus the theoretical distribution throughout this course as we look at different questions related to distributions.